Good afternoon, everyone. My name is Shomik Sarkar, and I have Aditya Balu with me. We are both from Iowa State. So we're going to discuss another application for distributed deep learning at scale, namely a topology optimization problem for additive manufacturing. So these are joint work with our colleague Professor Adarsh Krishnamurthy at Iowa State, as well as our students Jaideep, Ethan, and Anushrut, and scientists from RocketML, Santi, and Sergio. So begin with um let me begin with a little bit about ourselves. So I run a self-aware complex systems lab at Iowa State, and you can see this is us in the COVID time. We working pretty much remotely the whole time. So we develop machine learning and deep learning algorithms for a variety of engineering problems, industrial problems, and in general cyber physical systems problems. We collaborate with a lot of folks, including RocketML quite heavily. And these are some of our sponsors. We work with, the entire range of federal, state, and industrial projects. And as a matter of fact, this particular work kind of initiated in collaboration with ANSYS. So now, in terms of research area, we work in various different areas, including AI-driven design, AI-driven transportation, robust learning, and AI-driven agriculture. The two areas that are most relevant for today's talk is the notion of AI-driven design and manufacturing, and how do you do distributed and decentralized deep learning. So with that, let me contextualize the area that we'll be talking about today. So the area of AI-driven materials design and manufacturing essentially can be thought of based on two axes. So the one axis is a physics axis. We're going from simple physics to very, very complicated physics described by partial differential equations. On the other hand, we can also think from a geometrical standpoint, where we could think of simple geometry, like a drilled holes and a small, and sharp corners and things like that, to very complicated geometrical features as you go higher and higher resolution. So these are different works that we have done over the past few years in the intersection of deep learning and design and manufacturing. So, for example, our work initiated with an NSF project for machine learning for design for manufacturability that you see at the very bottom left corner, and then it went all the way at the complex physics scale to neural PDE solvers, where we are trying to build generative constraint generative models for solving PDEs in a fast and agile manner. On the other end, we are looking at very complex geometrical properties of CAD models and designs. So one of the prime example of we are looking at hard valve, artificial hard valve design. Today, the topic that we wanted to discuss is the notion of structural topology optimization. So how do you optimize the topology of a structure in order to minimize material usage and many other optimization goal that you may have. So this kind of lies in the middle of in the physics axis, where it has some complexity. But in terms of geometry, we started off with a simpler geometry, and now we are moving and more in a complex geometry, where we are looking at a high resolution designs, which also means that we are looking at more intricate and complicated geometrical features. So now our talk today will be, distributed in four, four parts. So I'll talk mainly about give you a sense of the notion of topology optimization for additive manufacturing, and then how do we use a deep learning framework to do this. And then Aditya will come in and discuss some of the key methodologies to scale this up, and present some results that we are very excited about. So to begin with, the notion of topology optimization is that we want to optimize a particular design such that we achieve some objective. And the notion of structural topology optimization, usually looks for to reduce material usage and to make things light to make parts less expensive, and so on. So as you can imagine, naturally there is an extremely important area of work in the aerospace industry, because they of course need much lighter material, but at the same time can do the job. And but it, of course, it is becoming increasingly used and more useful in other sectors as well, namely automotive in car design, in biomedical device design, and also in oil and gas applications, where the undersea and subsea the rigs that you want to make, you want to make sure that it has optimal designs. Now, apart from the structural topology optimization that we are talking about today, there are many other topology optimization that you can think of to optimize mechanical properties, chemical properties, and or electrical properties, and so on. Okay. So with this, just I want to sort of bring everybody on the same page so that we understand what a traditional topology optimization or structural topology optimization algorithm works like. So we initialize our design domain. So we have a part that we have to design. So we need to understand what are the loads of this on this part. And then also we want to assign a target volume fraction. So how much material we actually want to get rid of. Okay, so we would, and of course this can be a hyperparameter where people can go back and change the target volume fraction to reduce, to make it even more lighter, or on the other side. Now we start with a finite element analysis, and to understand the stress and strain profiles on these parts depending on the load condition. And then what essentially these traditional algorithms do, they try to understand what are the sensitivities in terms of different parts and different parts of these particular design, such that if you remove certain material, whether it can still withstand the loads that it was bearing. So based on these gradients, the algorithm goes ahead and updates the design, and essentially goes back to the finite element analysis to see whether there is any major changes happen and which could lead to failure. If not, it continues doing that, and it keeps doing that until you reach the target volume fraction. So you converge, and once you do that, you come out of the cycle, and you produce the design. Now, as you can imagine, this analysis, the finite element analysis, and doing these updates, it involves running these models again and again in the loop. So this is a direct optimization strategy, which of course has the expensive part of function evaluation at every iteration. So so this tends to be quite slow in many cases, especially if you're talking about a large 3D part with very high resolution. Then running these types of iterative optimization could be quite expensive. So our idea is that, can we use machine learning to solve this problem, to make it more fast, make it faster and more agile, and so on. Now, what is the context of additive manufacturing? Well, additive manufacturing actually showed us the usefulness of this kind of topology optimization, which we can really use to essentially come up with any sort of highly intricate and complicated looking designs that are highly optimized topologies, but could be very difficult for subtractive manufacturing to even materialize, right? So but with additive manufacturing, we can actually do that. And this also leads to personalized optimal design. So, for example, you see a Nike shoe on the left and a hip implant on the right. These things can be designed in optimal fashion for a particular person or particular athlete, which can really enhance their performance. Now, with that, we in the rest of the talk, we'll be using a voxelized representation for our deep learning based structural topology optimization. And there is a precise reason why we went that route, why we chose a voxelized representation of parts to do this. Is essentially the traditional B-rep representation that mostly used for 3D printing or additive manufacturing. Often that leads to some defects that you may have had in the B-rep representation, which gets translated into the 3D printing process. So that's why there's a lot of manual, pre-processing and post-processing becomes required in order to avoid that. Instead, what we wanted to do is an end-to-end process which doesn't, have these types of problems, and that's one of the key reasons we go with voxelized representations of parts in order to do topology optimization and additive manufacturing subsequently. But on the other end, the flip side of this thing is that if you want to do direct printing, 3D printing with this voxelized representation, you need high voxel resolution. So you need many voxels for parts, but because then only you will have high quality of print. As you can see in the figures that we have. So if you have a particular part here, and if we have a 32 cube resolution, you can really, you can see that the part is quite different from what you would typically envision. When you go to 64 cube, it starts looking like the part that we would like to have, and then at 128 cube is really matches the part that designer would design. But with these high voxel resolutions, of course, you deal with much higher training time for your machine learning model. At the same time, you have memory and computing resources issues, and that's where you need techniques to scale these things up so that we can handle this high resolution of voxelized representation. And that's where the distributed deep learning technologies and other types of parallelizing technologies which come into play that we are talking about today. Now, in terms of specifically what deep learning based methodology that we are using, as I already talked about, that traditional methods would have function evaluation at every iteration, and which becomes computationally very expensive. So we look at it for a very simple supervised learning approach. Now, although that's what we're going to present today, but you can look at this problem from many different learning problem point of view. You can think of it as a generative modeling problem. You can think of it as a reinforcement learning problem. But today we are focusing on a simple structural topology optimization framework based on supervised learning, where your input is your original initial design, essentially the domain, the full domain with all sorts of loading conditions. And if you have a trained deep learning based topology optimizer, the output that you are going to expect is an optimized geometry. So we have worked with many different deep learning architecture to make this happen. The one that we're going to present today, we use a UNet architecture, which we have found to be quite useful for these types of applications, which was extremely useful for segmentation type problems. Now, in this case, the inputs would be input compliance or input strain energy in this case, and also the target volume fraction, and the output is the final optimized geometry, optimized density. And in terms of the loss function, we use binary cross entropy. So at this point, I will hand it over to Aditya, who will take us through that how we actually train these models, and then more importantly for this particular tutorial, how we use different scaling up technologies or algorithms to make this happen for a very high resolution voxel representation. Aditya?
Thanks, Omik. So today we'll be, before we go into the details of the training, we will go into some details on how we generate the data. So we perform several simulations of topology optimization. So what we do in that is we initialize a geometry and then discretize it into tetrahedral elements, and then randomly choose 3 points where we apply the boundary conditions, which is the zero displacement, to keep the body to be rigid and fixed, and then we apply the loading conditions force at some nodes, and depending on the load locations, you get different kinds of topologies. So you perform topology optimization with the target volume fraction, and then we store all this information by performing voxel interpolation and keeping that value. So in total, in 2D, we have around 71,800 samples, and in 3D, we have 66,000 samples. So now, when we talk about voxelization or voxel interpolation here, we use a voxel resolution of 128 cubed. The previous best results we are aware of in this avenue is with 32 cube. And here we are trying for a challenging problem of 128 cube, which is necessary for performing additive manufacturing. At the same time, as Soumik mentioned earlier, there is the challenge of training this at high resolution voxel grids. So that brings us to the next topic, which is the methods for scaling to high resolution topology optimization. So we take twofold approach for scaling DLTO, or the deep learning based topology optimization, which we present here. The first approach we talk about is multigrid training, where we use the idea that training at lower resolutions is computationally cheap compared to using performing training at higher resolutions. And along with that, if you do transfer learning from the lower resolution model to a higher resolution model, then you get computational benefits while training at the higher resolution. In conjunction with the multi-grid training, we also use distributed data parallel deep learning for performing the training at using multiple nodes and in a CPU and GPU cluster. The reason of this is that when you go at lower resolutions, probably we can train it in probably one single GPU node or one single CPU node. But when we want to train for a high resolution as 128 cube, we end up facing several challenging issues with this CPU memory and the GPU memory. So that's why we use a conjunction of both multi-grid and the distributed data parallel deep learning. So in the multi-grid training, what we do is a progressive training at different resolutions. So say you start with a resolution of LC times LC squared, a 2D grid, and you train a network GNN for say mu1 epochs. Now, next we use the strain weights for training a 2LC times 2LC mesh, and then we train this for mu2 epochs, and then we go next to 4LC squared for mu3 epochs. So in total, if I want to formalize this idea, then if you want to train a network for an effective resolution of n squared, and you want to use a computational budget in such a way that you define the depth of your, how deep do you want to go in your multi-grid approach. Depending on the depth, you compute the LC, which we see on the right, and using the LC, we train mu dp epochs on that, and then slowly, progressively go all the way till training the final GNN on n squared resolution. So this approach uses the same weights which we learn in the lower resolution and then use it on the higher resolution. Now, the reason this works effectively is because we are using UNets, which is a fully convolutional neural network, and that helps us in achieving this with ease. We can also add additional layers when we are performing this, where we say you train on with a network unit with say depth 3 in LC squared. Then when you go for a unit with when you go for n by 4, you can probably add another layer to increase the depth from 3 to 4. That will improve the increase in the training performance, and that way we can do adaptive training all throughout and get better performance that way. So this is the multi-grid training, and in conjunction with the multi-grid training, we also look at distributed deep learning. So distributed deep learning reduces the overall training time for training, and in particular, why we need to care about it in the 3D topology optimization problem. We are dealing with 128 cube voxel resolutions, and practically with the current GPUs, it is very difficult to train using just one single GPU. In fact, a batch size of 16 for a unit will not even fit in the current GPUs which we are using. So because of that, we use the data parallel deep learning, which we have covered in this tutorial in detail. So in a brief idea, we just use the approach where we parallelize the like the forward and backward pass using different processes of MPI, and then do an all reduce for getting the gradient in the end. So now we look at the results which we get from both these methods which we use. So first, we look at the results we get from just multigrid. And for validation, we do this in 2D. So what we try to do here is we train a full 512 squared like a domain training where we do use a 2D unit and train using the binary cross entropy loss. And that's the full 512 squared which you see in the bottom. And we use a multigrid approach where we start training in 32 squared and then progressively go all the way till 512 squared. So when we look at the test loss plot, which you see in the left, you see that the full training takes about 100 epochs to reach the same loss, which we are able to get in with just 40 epochs of training in the multigrid approach. And the same way, the accuracy is also almost the marginally with some marginal difference. We have the same accuracy as whatever we get from the full 512 square training. Also, we see that the time taken for training a multigrid is 3 times lesser than the time taken for doing a full training in 512 square. So this gives us a motivation on how we can move towards using the same idea in 3D. So that's where we do the multigrid training of DLTO in 3D with the highest resolution being 128 squared. We start with 32 cubed and then progressively train 64 cubed and 128 cubed. Just like in the previous slide where we saw in 2D, we got 3x speed up. Similarly, here also we obtain a 3.1x speed up from the multigrid training. Next, please. So to summarize the scaling which we are obtaining here, while we show the multigrid scaling of 3x, there is an unknown factor which is not mentioned in those slides, that the training is also already performed using distributed deep learning. In other words, for 128 cubed and 64 cubed, we cannot train on a single CPU or GPU node. So we account for that by performing distributed deep learning. So again, to get some sense of how much are we scaling by using distributed deep learning, we look at the plot on the right, where we use 8 processes for performing training 1 epoch. So it takes around 160 seconds for 160 minutes for training on 8 processes. Whereas when we go with 64 processes, this goes down to all the way to 20 minutes for 1 epoch. Remember this is 128 cubed performed on a CPU node, whereas on a GPU node, we could get better performance, but with lesser batch size. So for fitting the batch size which we need, we are using a CPU node here. Finally, this is just that when we use the distributed deep learning as a scale up of 9x, along with the multigrid scaling of 3x, the total time to train the model is 27x, because we are using both of them in conjunction with each other. And then when we look at the time to inference, it takes 200 milliseconds to obtain 1 forward pass to get the optimized design. And then once you get the optimized design, when we want to 3D print it, it takes around 1.5 hours to finally get the optimized design. So next slide. So here's some visualizations on the 3D designs which we were looking at. So on the left, the 2 designs which we show here is just a simple cube, which is having a special loading condition and boundary conditions which were not present in neither the train or the test set. Specifically, in this case, we have 4 boundary conditions and 2 loads in the first case, and then 4 boundary conditions and 1 load in the second case, which is not there in the training set at all. And the target is what we obtain from the topology optimization process, traditional topology optimization process. And the rightmost is what we predict using our 3D unit approach, which we just mentioned, the 3D DLTO. And we see that we are able to obtain very similar looking shapes to whatever the target shapes are. Next slide, please. So not just have we able to like get the optimized shapes, we are able to even 3D print it using direct voxel printing. So the right side shows the as manufactured optimal design, which we get using 3D printing. And left side is just a time lapse on how we 3D print this in our lab. So we use a simple like direct voxel printing approach, which we mentioned in the beginning, to get these prints. Next slide, please. Yeah, so in conclusion, in this talk, we presented topology optimization for additively manufactured designs using deep learning. And then we also motivated our problem on how we need to train for high resolution voxel grids. And we show performance of like scaling using both multigrid and distributed deep learning in conjunction, and obtain around 27x speed up in the time to train a deep learning model, and then are able to perform quick inference using the trained model to quickly 3D print these designs. In terms of future work, we would like to extend this to scale for arbitrary CAD geometries and much more complex geometries, while also reducing the data requirements for performing this training using some other approaches like reinforcement learning or generative approaches. And next, here are a few acknowledgements of the funding resources and the compute resources. So major part of the simulations were run on Bridges 2 from Pittsburgh Supercomputing Center, which we use for running our HPC like distributed training here.
Thanks, Aditya, and thanks everyone for your attention. I would be happy to answer any questions that you may have. Thank you.